The brightest, coldest, most lifeless-looking object in the entire solar system may also be the most alive. It is a moon barely 300 miles across, wrapped in ice so reflective it shines brighter than fresh snow, sitting 900 million miles from the sun, where nothing is supposed to stay warm or wet. By every rule we thought we understood, it should be frozen solid, all the way through, a dead relic left over from the birth of the planets. And yet it is erupting, firing an entire ocean's worth of water into space through cracks near its south pole continuously, tonight. And when we finally reached out and tasted that spray, we did not just find water, we found the chemistry of living things. So how did a world this small, this cold, this far from any star, become the best place we know of to go looking for life beyond the Earth? Get cozy and settle in, subscribe if you have not already, and stay with us, because the story of this little moon quietly overturns almost everything we once assumed about where life is allowed to exist. Let's dive in. Part 1. The telescope that looked. Somewhere out beyond the orbit of Jupiter, near the ringed planet that has stood at the edge of every child's idea of space, there is a small frozen moon that has spent its entire existence pretending to be dead. It is white, it is silent, and it is colder than almost anything you have ever imagined. For most of the time that human beings have owned telescopes, it was nothing more than a faint speck of light beside Saturn, a rounding error in the count of that planet's many moons. Nobody expected anything from it, and then, in the autumn of the year 2022, we pointed the most powerful eye humanity has ever built directly at that speck, and it showed us something that, by every rule we thought we understood, should have been impossible. The eye was the James Webb Space Telescope, a machine the size of a tennis court that sits 1 million miles from Earth, chilled to within a whisper of absolute zero so that it can see the faint infrared warmth of the universe. It was designed to look at the first galaxies, at the atmospheres of distant worlds, at the oldest light in existence. But on this particular observation, it turned its attention much closer to home, towards Saturn, and toward a moon so small that you could set it down inside the borders of the state of Arizona and still have desert left over. That moon is named Enceladus, and when Webb looked at it, it did not see a dead pebble of ice. It saw a fountain. Rising off the south pole of that tiny world was a single continuous jet of water vapor, and the size of it is the part that breaks the mind. The plume stretched more than 6,000 miles out into space. Let me give you that number in a way you can actually hold. 6,000 miles is roughly the distance from Los Angeles to Buenos Aires, from the western coast of the United States all the way down past the equator to the far side of South America. Now picture that entire distance drawn as a single column of mist, erupting from a ball of ice barely 300 miles across. The plume was not a little larger than the moon. It was 20 times longer than the moon was wide. It was as if a stone the size of a city had opened a crack and breathed out a cloud that stretched across a continent. And it was not a one-time event. It was not a fluke, not a burst, not something Webb happened to catch on a bad day. The telescope measured the rate at which this frozen moon was pouring water into space, and the answer came back at around 300 litres every second, close to 80 gallons of water per second, flung continuously off the surface of a world where the temperature sits at 330 degrees below zero on the Fahrenheit scale. A moon that cold should be locked solid. Ice at that temperature is harder than most rock. There should be nothing to erupt, no liquid to spray, no engine to drive it. And yet there it was, caught in infrared light from nearly 1 billion miles away, quietly and relentlessly emptying itself into the dark. That is the impossible thing the telescope found. Not a signal, not a message, not a flying saucer. Something stranger and in its own way, far more important. It found a small, dead-looking world that was unmistakably physically alive with motion, breathing an ocean out into space in a plume you could see from the distance of another planet. And the obvious question, the one that has driven scientists half out of their minds with curiosity for the last 2 decades, is the one we're going to follow all the way down tonight. Where is that water coming from? What is keeping it warm enough to be water at all, out there in the cold and the dark so far from the sun that our star is barely more than a bright point in the sky? And once you understand where the water comes from, a second question opens beneath the first one, quieter and much larger. The kind of question that does not let you sleep once you have heard it. Because the water is not just water. It never was. To understand why a plume of mist off a frozen moon might be the most important thing the James Webb Space Telescope has ever photographed, you have to understand how badly we misjudged this little world to begin with. You have to understand just how dead it was supposed to be. For a very long time, everything we knew about Enceladus told us to ignore it, and everything we assumed about the outer solar system told us that oceans and warmth and the machinery of life belonged close to the sun, on worlds like ours, and nowhere else. Webb's fountain was the loud, undeniable confirmation of a secret that a different spacecraft had begun uncovering years earlier, a secret that rewrote the map of where life could exist. But before we can appreciate the size of that secret, we have to go back to the moon itself, and to just how convincingly it wore the mask of a corpse. Consider how improbable the observation itself was, because it sharpens the wonder. The James Webb Space Telescope was not built to stare at moons. It was designed to capture the faintest infrared light in the universe, the warmth of galaxies so far away that their light has been travelling toward us for most of the age of the cosmos. To do that, it has to be kept colder than almost anything, shaded from the sun behind a sunshield the size of a tennis court, chilled to within a few dozen degrees of absolute zero so that its own heat does not blind it. And it sits not in orbit around the Earth, but a full 1,000,000 miles away, 4 times farther than the moon, in a special balance point in space where it can hold steady and stare into the dark. This is the machine we turned for a brief window toward a small moon of Saturn, and the thing it saw was so large, relative to its source, that at first it is hard to trust. When Webb looked at Enceladus, the moon itself was a tiny point, barely resolved at that distance. But the plume of water vapour coming off it was enormous in the telescope's infrared vision, a great glowing cloud of water reaching out many times the width of the moon, because water vapour shines brightly in exactly the kind of infrared light Webb was built to see. The telescope could measure how much water was in that cloud, how fast it was moving, how far it stretched, all from nearly 1,000,000,000 miles away. We did not have to go there to know the moon was erupting. We could read it in the light, the way you can read the steam rising off a cup across a room and know, without touching it, that the coffee inside is hot. There is a quiet irony worth naming at the very start of this journey. We built a telescope to look at the beginning of the universe, at galaxies so distant they are almost the edge of what can be seen, and one of the most startling things it has shown us is not far away at all. It is here, in our own solar system, on a moon we have known about since the 1700s. Sometimes the most extraordinary discoveries are not the ones that require reaching farther out, but the ones that come from finally looking closely at something we thought we already understood. Enceladus had been sitting there in Saturn's family the whole time, catalogued, named, dismissed. It took the sharpest eye we ever made to reveal that we had been wrong about it for centuries. Keep that image with you as we go, the fountain rising silently off the tiny bright moon, because everything else in this story is really an attempt to explain it. A frozen world smaller than some countries, so cold its ice is hard as stone, throwing a plume of water taller than a planet is wide out into the vacuum, continuously, tonight and every night. It should not be possible. And the fact that it plainly is possible is the thread we are going to pull, patiently, all the way down through the ice and into the sea below, following it to a question far larger than any moon. So let me take you there first. Let me show you the deadest-looking world we have ever found, and let me show you why, for so long, not a single scientist on Earth thought to look at it twice. Part 2. The Little White World. Imagine, for a moment, that you're approaching Enceladus for the first time, drifting in towards Saturn from the outer dark. What you would see is a small, almost perfectly white sphere, so bright it is difficult to look at directly. It is one of the most reflective objects in the entire solar system. Its surface is made of nearly pure water ice, clean and fresh and smooth in places like a skating rink, and that ice throws back close to 99% of the sunlight that lands on it. Scientists measure this with a number called albedo, which is simply how much light a surface reflects, and Enceladus has a geometric albedo of about 0.99. That is almost a perfect mirror. Fresh snow on Earth, the brightest natural thing most of us ever see, reflects far less. This moon is brighter than snow. That brilliance is beautiful, but it is also a kind of curse, because a surface that reflects nearly all of the sunlight that hits it keeps almost none of the warmth, and out here there was very little warmth to begin with. Enceladus orbits Saturn at a distance of about 900 million miles from the Sun. At that range, our star, the fire that keeps every living thing on Earth alive, has shrunk to a brilliant point of light, delivering only 1/100th of the warmth we feel on a summer afternoon. So the little moon takes in a feeble trickle of sunlight and then reflects almost all of it straight back into space, keeping nothing. The result is a surface temperature of around 330 degrees below zero on the Fahrenheit scale. That is only about 75 degrees above absolute zero, the coldest temperature that physics allows to exist anywhere. At that temperature, water ice is not slushy or soft. It behaves like stone. You could carve buildings out of it. The moon itself is tiny. It measures just over 300 miles across, roughly 313 miles from side to side, which makes it one of the smaller round moons of Saturn. To give that a sense of scale, you really could fit the entire moon comfortably inside a single American state. Set Enceladus down over Arizona, and its edges would not quite reach the state lines. Everything you have ever heard about worlds that harbour oceans, worlds that run engines of heat far down inside themselves, worlds that might cradle living things, involves bodies far larger than this. Planets. Big moons. Enceladus is a marble. Its gravity is so weak that if you could stand on its surface, a gentle hop would carry you as high as a building, and a hard throw might send a rock off the moon entirely, never to come back. So put yourself in the position of a scientist looking at this world through the eyes we had before we ever sent a spacecraft close. What you would see is a small, blinding white ball of frozen water, hundreds of degrees below zero, far too little to hold on to any real internal heat, so far from the sun that sunlight is almost meaningless, with barely enough gravity to keep dust on its surface. By every reasonable measure, it should be one of the most thoroughly, permanently dead objects imaginable. A frozen leftover from the birth of the solar system, unchanged for billions of years, waiting out eternity in the cold. When the first missions began planning their tours of Saturn, Enceladus was not high on anyone's list. There was nothing there. Everyone knew there was nothing there. And this is the first lesson of the whole story, the one worth carrying with you as we go, because we are going to return to it at the very end. Appearances, at the scale of worlds, are treacherous. The brightest, coldest, most inert-looking surface in the entire neighbourhood of Saturn was a lid. It was a mask. Underneath the frozen shell, hidden completely from every telescope and every early expectation, something was waiting that would overturn our sense of where life could live. But nobody knew that yet, because the only way to find out was to go, and to look closely, and to be paying attention when the numbers came back wrong. Let me set you down on that surface for a moment, before we break the illusion, so you can feel the mask for yourself. Picture standing on the south pole of Enceladus. Beneath your boots is a plain of ice so white it glows, stretching flat and hard to a horizon that curves away sharply because the world is so small. Above you, filling a huge portion of the black sky, hangs Saturn itself, its bands of gold and cream turning slowly, its rings cutting a bright thin line across the dark. The sun is there too, but it is only a very bright star, and it gives your skin nothing. There is no air, there is no sound, there is no wind. It is the stillest, coldest, most silent place you can imagine, a frozen churchyard at the edge of a giant's kingdom. And then, a few miles away, the ground opens. To feel how small this moon truly is, hold it against the worlds you already know. Our own moon, the one that lights your night sky, is about 2,160 miles across. Enceladus, at just over 300 miles, is roughly 1/7 of that width, small enough that 7 Enceladuses lined up side by side would barely span our moon. And against the Earth, at nearly 8,000 miles across, it all but disappears, a chip of ice next to a boulder. This is not the kind of body we expected to run an ocean and a furnace. Small worlds are supposed to be simple, cold, and finished. Their internal fires long since gone out, because small things lose their heat quickly. Everything about the size of Enceladus said it should be inert, and that near-perfect brightness, that albedo of about 0.99, is worth pausing on, because it is not an accident. A surface stays that clean and reflective only if it is constantly being refreshed. On most old, dead worlds, The surface slowly darkens over billions of years, dusted and battered and chemically weathered until it turns grey and dull. Enceladus is not dull. It is the brightest large body in the solar system, and the reason, we would eventually understand, is that it is perpetually snowing on itself, its own geysers dusting the surface with a fresh coat of clean ocean ice. The very brilliance that made the moon look so dead was, all along, a clue that something beneath it was still alive and resurfacing it from within. We were looking at the evidence the entire time and reading it exactly backward. It helps to picture the sky above that frozen surface, because it is unlike anything on Earth. Saturn itself would hang overhead, not as the small pale dot we see through a backyard telescope, but as an enormous banded wall filling a huge stretch of the black, its rings slicing across the view as a razor-thin line of light. Enceladus is so close to Saturn, only about 148,000 miles out, that the planet dominates its sky the way nothing dominates ours. To stand on that ice would be to stand beneath a permanent silent giant, its stripes of gold and cream turning slowly through the long dark, while the true sun, the source of all the warmth we know, shrank to a single bright point lost among the stars. And here is the thing to remember about masks. A mask works because it tells you to stop looking. The blinding whiteness of Enceladus, its perfect frozen stillness, all but instructed generations of astronomers to move their attention elsewhere, to the storms of Saturn, to the rings, to larger and more obviously interesting moons. The disguise was not just convincing, it was actively discouraging. It took an accident, a magnetic reading that refused to make sense, to make anyone look past the mask at all. And that should make you wonder, quietly, how many other masks are out there in the dark? How many other dead-looking worlds are waiting for someone to be surprised by them? Without a whisper, because there is no air to carry sound, a wall of white vapour and glittering ice crystals erupts from a long crack in the surface and roars upward past you, climbing so fast and so far that it does not slow, does not arc, does not fall back. It simply rises, straight up, until it vanishes into the black overhead and keeps going into space. You're standing on a frozen shell 300 degrees below zero, and something warm and wet is firing straight up through it, out of the ground, into the vacuum. The deadest-looking world you have ever seen is doing something that only a living, working, warm world should be able to do. And that impossible sight, that fountain rising out of a corpse, is exactly what the first spacecraft to visit stumbled into, entirely by accident, when it noticed that something invisible was pushing back against the magnetic field of Saturn itself. That is where the mask began to crack, and it started not with a picture, but with a needle twitching on an instrument nobody was watching very closely. Part 3. The anomaly nobody expected. The spacecraft that broke the story open was named Cassini, and it arrived at Saturn in the middle of the year 2004 after a journey of nearly 7 years across the solar system. It was one of the largest and most capable robotic explorers ever built, about the size of a school bus, packed with cameras and spectrometers and instruments designed to study the ringed planet in every way we knew how. Its mission was to map Saturn's weather, to probe the structure of its famous rings, to measure its enormous magnetic field, and to survey its family of moons. Nobody sent Cassini to Saturn to find an ocean of liquid water on a 300-mile ball of ice. That possibility was not seriously on the table. Enceladus was just one more moon to photograph on the way past. But early in the mission, as Cassini swung through the Saturn system, one of its instruments began returning a reading that did not fit. The instrument was a magnetometer, a device that measures magnetic fields, and Saturn has an immense one, a magnetic bubble far larger than the planet itself that all of its inner moons travel through. As a rule, when a small dead moon passes through a planet's magnetic field, it barely disturbs it. A lifeless rock is more or less transparent to a magnetic field. The field lines pass through and around it as if it were not there. That is what should have happened at Enceladus. Instead, the magnetometer found that Saturn's magnetic field was bending, bowing, and draping itself around the little moon, deflecting as though it were flowing around an obstacle in a stream. Something near Enceladus was physically pushing back against one of the largest magnetic fields in the solar system. That made no sense for a dead rock, and the scientist on the mission knew it. A bare ball of ice cannot deflect a magnetic field like that. The only way to bend the field the way Cassini was seeing was if there were gas and fine dust in the space immediately around the moon, an invisible haze of charged particles loading down the field lines and dragging them out of shape. But where would gas around a frozen moon come from? Frozen worlds are not supposed to have atmospheres. They are too cold and too small to hold on to gas, and yet the field was bending over and over every time the spacecraft came near. The anomaly was real, it was repeatable, and it demanded an explanation. So the mission planners did the only sensible thing. They decided to send Cassini in for a much closer look, to fly it low over the surface of this moon that was suddenly, quietly, refusing to behave like the dead thing everyone had assumed it was. What Cassini found when it looked closely is one of the great surprises in the history of planetary exploration. Down near the south pole of Enceladus, cutting across that blinding white surface, were 4 enormous parallel fractures, long straight canyons gouged into the ice, each of them roughly 80 miles long and a couple of miles wide, running side by side like the marks of an immense claw. Because of their appearance, the scientists nicknamed them the tiger stripes. Later they were given formal names, drawn from an old book of tales of the Middle East, and so today those 4 canyons on a moon of Saturn are called Alexandria, Cairo, Baghdad, and Damascus. And when Cassini measured the temperature along those stripes, it found that they were warmer than the surrounding terrain. On a moon that should have been the same lethal cold everywhere, there were 4 long wounds near the South Pole that were leaking heat. And they were not just leaking heat, they were erupting. From those 4 canyons, Enceladus was firing continuous geysers of water vapor, tiny ice particles and gas, straight up off the surface at speeds of over 800 miles per hour, hundreds of miles into space. Cassini flew where no one had thought to send it, and found a frozen moon behaving like a shaken bottle of soda, jetting material out of cracks in its crust so violently and so continuously that the moon's own feeble gravity could not hold on to most of it. The stuff being erupted was moving fast enough to escape Enceladus entirely, spraying out into orbit around Saturn. This was the source of the gas that had been bending the magnetic field all along. The moon was venting itself into space, and it had been doing so invisibly the entire time we'd been dismissing it as dead. There is a detail here that turns the strange into the sublime, and it is worth slowing down for. All that ejected material, all those ice crystals thrown off the surface at hundreds of miles an hour, does not simply vanish. It spreads out along the moon's path around Saturn and forms a faint wide ring, the outermost of Saturn's rings, known as the E-ring. For decades, astronomers had seen that diffuse outer ring and wondered where its material came from, because rings should slowly dissipate over time unless something keeps resupplying them. Cassini solved the mystery. The E-ring is made, in large part, of Enceladus. It is frozen ocean water, sprayed off a single small moon, spread out into a halo that circles an entire planet. This little world is quietly, endlessly paving its own orbit with the frozen water of a hidden sea. Hold on to that image, because it is going to matter a great deal later, when we realize that a moon which sprays its ocean into space is a moon that is, in effect, mailing us samples of itself. It is worth appreciating just how easily this discovery could have been missed. The magnetic anomaly was not a flashing light or an alarm. It was a subtle bend in a set of numbers, a distortion in the shape of a field that only made sense if you were paying close attention and willing to be surprised. A less curious team might have filed it away as noise, an instrument glitch, a rounding error, and moved on to the planet and the rings that Cassini had actually been sent to study. Instead, the scientists trusted the anomaly enough to spend precious mission time and fuel redirecting a school bus-sized spacecraft to fly close to a moon nobody had cared about on the strength of a magnetic hunch. That willingness to chase the thing that did not fit is how nearly every great discovery in science actually happens. And when Cassini did fly close, the sight of those 4 glowing fractures near the South Pole was genuinely unprecedented. Geologic activity, real ongoing activity, on a body that small had been considered essentially impossible. The Earth is geologically alive because it is large and still hot inside. Small icy moons were supposed to have frozen through to their cores eons ago, their internal engines long dead. To find 4 warm, actively erupting canyons on a 300-mile ball of ice was like finding a working fire in a house that had stood abandoned and cold for 1,000 years. It did not just add a fact to the catalogue, it broke a rule we thought we understood, and it forced a question that would take another 2 decades to answer. What, on a world this small, could possibly still be generating heat? The names given to those 4 fractures carry a strange poetry of their own. Alexandria, Cairo, Baghdad, and Damascus, 4 ancient cities of the desert, scrawled across the coldest terrain humanity has ever mapped, on a moon where the temperature never rises anywhere near the point where water could pool on the surface. It is the sort of naming that reminds you how human this enterprise is, how we reach into the outer dark and label what we find with the oldest words we have, as if to keep the strangeness company. And beneath those 4 named wounds, all along, ran the passages that connected the surface to a sea, the cracks through which an entire hidden ocean was quietly breathing itself into space. The whole sequence is a reminder that the outer solar system is not the finished frozen museum we once imagined it to be. It is a place where things are still happening, where worlds are still warm inside, still cracking and venting and reshaping themselves, still running engines we did not know they had. Enceladus was the first clear proof that a body that small, that far out, that cold on the outside, could be geologically alive, and it opened the door to a new way of seeing the entire region beyond the giant planets. Not as a graveyard, but as a territory of hidden fires and buried seas, most of them still waiting to be found. But all of this raises a question that only sharpens the more you think about it. Water vapour was firing out of those cracks. Not ice being knocked loose, not dust being stirred up, but water vapour and fine grains of ice, the unmistakable signs of liquid water reaching the surface and flashing away into space. And here is the problem. Liquid water cannot exist on the surface of Enceladus. It is far too cold. Any water exposed to that surface would freeze instantly into stone or boil away into the vacuum. So if water was coming out of the ground, then it had to be coming from somewhere below the ground, somewhere warmer, somewhere the killing cold of the surface could not reach. The geysers were not just a curiosity. They were a message written in mist across the sky, and the message said something that should have been impossible. Somewhere beneath the frozen shell of this dead little moon, there was liquid water, and where there was liquid water there had to be heat. The only question was how much, and how far down, and what, exactly, it was keeping warm. Part 4. The Ocean Beneath the Ice. When you see water vapour pouring continuously out of a frozen world, you are looking at a signature, a kind of proof written directly into the sky, and the proof is this. There is liquid water down there, on a surface at 330 degrees below zero. Nothing wet can survive in the open, so the fact that wet material keeps arriving at the surface and blasting off into space means that somewhere below the ice, protected from that lethal cold, there is a reservoir of liquid feeding the geysers. The plumes are a straw dropped into a hidden drink. But how much liquid, and how far down, and shaped like what? A few isolated puddles trapped in the ice? A buried lake, or something larger? That was the question Cassini spent years of careful flybys trying to answer, and the answer, when it finally came, was almost too large to believe. To measure something you cannot see, hidden under miles of ice, you have to be clever, and the scientists on the Cassini mission were. They used 2 independent methods, and both pointed to the same astonishing conclusion. The first method was to watch the moon's rotation with extraordinary precision. As Enceladus travels around Saturn, it does not spin perfectly smoothly. It rocks, very slightly, back and forth, a tiny wobble in its rotation that scientists call a libration. And here is the beautiful part. The size of that wobble depends on what the inside of the moon is like. If Enceladus were frozen solid all the way through, a single rigid ball of ice and rock, it would rock by one specific small amount. But if the outer shell of ice were floating freely, disconnected from the rocky core below, sliding on a layer of liquid in between, then the shell would wobble by a noticeably larger amount, the way a raw egg spins differently from a hard-boiled one because the liquid inside sloshes. When Cassini measured the wobble, it was too large for a solid moon. The icy shell of Enceladus was not attached to its core, it was floating. The second method was to measure the moon's gravity. As Cassini flew close to Enceladus, the moon's gravity gave the spacecraft the tiniest of tugs, speeding it up and slowing it down by fractions of a millimeter per second. And by tracking those minuscule changes in the radio signal from the spacecraft, scientists could map how mass was distributed inside the moon. What they found was that the density beneath the South Pole was consistent with a layer of liquid water denser than ice, sitting between the frozen shell and the rocky interior. Two completely different measurements, the wobble and the gravity, told the same story. And so the conclusion became unavoidable, and it reshaped our entire picture of this world. Enceladus is not a solid ball of ice. It is a rocky core, wrapped in a global ocean of liquid salt water, wrapped in turn by an outer shell of ice. The whole moon is layered like that, all the way around, a worldwide sea sealed beneath a frozen crust. Let me try to give you the true dimensions of this, because the numbers deserve to land. The ice shell that covers the ocean is, on average, something like 12 to 15 miles thick, though it thins dramatically near the South Pole, down to only a few miles, which is why the geysers erupt there and nowhere else. That is the thin spot, the place where the cracks reach down close enough to the ocean to let it escape. And the ocean beneath that shell is not a shallow film. In places it may run as much as 6 miles from the underside of the ice down to the seafloor. 6 miles of liquid water. To put that against something familiar, the deepest trench in all of Earth's oceans, the Mariana Trench, plunges to about 7 miles at its lowest point. The ocean of Enceladus, on a moon you could tuck inside Arizona, is nearly as far from top to bottom as the deepest place on our entire planet. This is not a puddle. It is a genuine worldwide sea, and by some estimates it holds a volume of water comparable to some of Earth's own seas, all of it wrapped around the inside of a frozen marble at the edge of the Saturn system. Now stop and let the strangeness of that settle over you, because we have arrived at something that genuinely rearranged how scientists think about the universe. For most of the history of the search for life, we operated on a simple and reasonable assumption. Liquid water needs warmth. Warmth comes from the sun, and therefore liquid water, and any life that might depend on it, must exist only in a narrow band of comfortable distance around a star, a region scientists literally call the habitable zone. Get too far from the star and everything freezes. Enceladus is 900 million miles from the sun, 10 times farther out than the Earth, far out in the frozen territory where, by that old logic, nothing should be wet and nothing should be warm. And yet here is a global ocean of liquid water, kept from freezing for what may be billions of years, in exactly the place the rules said an ocean could not be. The discovery did not just add one more interesting moon to the catalogue. It suggested that the warm, wet places in the universe might not be rare islands close to stars at all. They might be hidden everywhere, tucked under the ice of countless cold moons, out in the dark where we never thought to look. But an ocean that exists where it should not exist demands an explanation. Something is keeping 6 miles of water liquid in a place where the temperature at the surface is 330 degrees below zero and the sun provides essentially nothing. Water does not stay liquid on its own out there. Left alone, that entire ocean would freeze solid, from the seafloor up, until Enceladus was exactly the dead frozen ball everyone first assumed it to be. So something is fighting that freeze, continuously, and has been fighting it for an immense span of time. There is a furnace burning somewhere inside this little moon, an engine of heat with no sunlight to feed it and no fire to fuel it. And understanding what that engine actually is means understanding one of the most elegant and surprising tricks in all of physics. Because the thing keeping the ocean of Enceladus warm is not heat in any form you would recognize. It is gravity. It is the simple, endless pull between worlds, turned into warmth by nothing more than motion. The egg comparison is worth dwelling on, because it captures the cleverness of the method perfectly. If you spin a hard-boiled egg on a table, it spins smoothly as one solid piece. If you spin a raw egg, it wobbles and stops strangely, because the liquid inside sloshes and drags against the shell, moving at its own pace. Scientists could not crack Enceladus open, but they could watch how it spun, how it rocked back and forth as it orbited, and from the size of that wobble they could tell whether the inside was solid or liquid, exactly the way you can tell a raw egg from a cooked one without breaking the shell. The wobble was too large for a solid moon. The shell was sloshing on a hidden sea. It is a beautiful piece of detective work, reading the insides of a world from the wobble of its outside. There is one more detail that turns suspicion into near certainty, and it is the salt. When Cassini analysed the ice grains in the plume, it found they were salty, carrying the same kinds of salts dissolved in Earth's own oceans. That mattered enormously, because pure ice, simply melted, would not be salty. Salt in the water means the water has been in contact with a rock, dissolving minerals out of a seafloor over long stretches of time, exactly as our oceans have leached salt from the continents and the ocean floor. The saltiness of the plume was proof that the ocean of Enceladus is not some sterile pocket of meltwater trapped in the ice, but a genuine sea sitting on rock, chemically connected to the mineral world below it, the kind of sea where interesting chemistry, and perhaps more than chemistry, could unfold. The word ocean can be misleading, so it is worth being clear about what kind of ocean this is. It is not a small trapped lake, not a slush of half-frozen mud, not a few isolated pockets of brine. It is a single body of liquid salt water that wraps all the way around the rocky core of the moon, a global sea continuous from pole to pole beneath the ice. Every point on the seafloor of Enceladus is connected to every other point through that one worldwide ocean. Whatever chemistry happens at one vent can, in principle, spread through the entire sea. That global connectedness matters, because it means the ocean is not a scatter of separate little experiments, but one large, mixed, chemically unified environment, the kind of place where a process that begins in one spot has the whole moon's ocean to spread into. Whenever you feel the scale of it start to slip away, come back to one image. A moon you could set down inside a single desert state, holding a sea nearly as far from surface to floor as the deepest trench on Earth, wrapped in ice, warmed from within, sealed in darkness, 900 million miles from the nearest sunlight worth the name. That is not a diagram in a textbook. That is a real place, out there right now, as real as the ground beneath you, and its ocean has been sitting in the dark, liquid and moving since long before anything on Earth grew a backbone. The universe was keeping a sea for us to find, and it hid it in the last place we thought to look. And to see how a pull can become a fire, we have to look at the company Enceladus keeps, and at the strange gravitational dance it has been locked into with a neighbouring moon for longer than there has been complex life on Earth. Part 5. The Furnace with No Sun. Enceladus does not travel around Saturn alone. It shares the crowded space near the ringed planet with a whole family of other moons, and one of them, a larger moon named Dione, holds the secret to how the ocean stays warm. Dione orbits Saturn farther out than Enceladus does, and the two moons are bound together in a relationship that astronomers call an orbital resonance. The word sounds technical, but the idea is simple and rhythmic, almost musical. For every single orbit that Dione completes around Saturn, Enceladus completes exactly 2. 2 laps of the little moon for every 1 lap of the big one, over and over, with the precision of a metronome. This 2-to-1 ratio means that the two moons keep meeting up at the same points in their orbits, again and again, and every time they line up, Dione's gravity reaches out and gives Enceladus a small repeated tug in the same direction. That regular tugging has a consequence, and it is the key to everything. Left entirely to itself, a moon will tend to settle into a lazy circular orbit, a smooth, even path at a steady distance from its planet. But Enceladus is not left to itself. Every time it swings past Dione and receives that little gravitational pull, its orbit is kept from relaxing into a circle. Instead, it is held slightly stretched, slightly oval, what scientists call an eccentric orbit. And a stretched oval orbit is a very different thing from a circular one, because it means the moon is constantly changing its distance from Saturn. On one part of its path it swings in closer to the giant planet, and on another part it drifts farther away, and then it comes back in and out again, once every single orbit, forever. That constant change of distance is the crack through which the heat pours in, and to see how, you have to think about what Saturn's gravity does to a moon that keeps changing how close it is. Saturn is enormous, far more massive than any of its moons, and its gravity does not pull with the same strength everywhere. It pulls harder on things that are closer and more gently on things that are farther away. So when Enceladus swings in towards Saturn, on the near part of its oval orbit, the planet's gravity grabs it more strongly, and because the near side of the moon feels a stronger pull than the far side, the whole moon gets physically stretched, elongated just slightly along the line pointing towards Saturn, like a ball of dough being gently pulled at both ends. Then, as Enceladus swings back out to the far part of its orbit, the pull eases, and the moon relaxes back toward round. In towards Saturn, stretch. Out away from Saturn, relax. In, stretch. Out, relax. Every orbit, endlessly. The entire body of the moon, rock and ice and ocean, is being kneaded, squeezed and released in a slow, planet-wide rhythm that never stops and never has stopped for an unimaginable span of time. And here is where a pull becomes a fire. When you flex something over and over, it heats up. You have felt this yourself. Take a paperclip or a piece of wire and bend it rapidly back and forth, and within a few seconds the metal at the bend becomes warm, even hot, because the internal friction of the material resisting all that flexing turns motion into heat. Enceladus is doing exactly that, but on the scale of an entire world, and it has been doing it continuously for a length of time, measured not in seconds but in billions of years. All that rhythmic squeezing and stretching generates immense friction far inside the moon's rocky core, where the rock physically grinds and shifts against itself, and that friction produces heat, steadily, from the inside out. Scientists call this process tidal heating, because it is driven by the same kind of tidal forces that raise the seas on Earth, and on Enceladus it functions like a colossal internal furnace. It warms the rocky core, and the warm core melts the ice above it from the bottom upward, maintaining that 6-mile ocean of liquid water against the killing cold, without a single ray of sunlight, in the darkest reaches of the solar system. I want you to feel this from the inside, because it is one of the most quietly extraordinary things in nature. Imagine you could sink down through the ice of Enceladus, into the black ocean beneath, and then imagine you could feel the whole moon as if it were your own body. As Enceladus swings in towards Saturn, you would feel the entire world lean and stretch, the rock beneath the sea groaning as it flexes, the seafloor itself bowing under the pull of the giant planet overhead, a slow tide moving not through water but through solid stone. Then, as the moon eases outward again, you would feel the whole world relax, settle, breathe out. And then the pull would come again, and again, once every orbit, a slow and patient kneading of an entire world that has been going on since before the first complex life crawled across the floor of Earth's oceans. It is not violent to feel. It is enormous and slow, a gentle, ceaseless rocking, and everywhere the rock rubs against itself in that endless motion, warmth blooms. The furnace that keeps this alien ocean liquid is not a fire and not the sun. It is the orbit itself, turned into heat. This single realization, that gravity alone can keep an ocean warm, is what changed the outer solar system from a frozen graveyard into a territory of possibility. Because if tidal heating can keep Enceladus liquid, then it can do the same for other moons in similar situations, and indeed we now suspect that hidden oceans lie beneath the ice of several worlds out there, warmed the same way by the flexing pull of a giant planet on a moon in an eccentric orbit. The sun, it turns out, is not the only way to keep water warm. It is not even the only common way, and the moment you accept that, the count of places in the universe where liquid water could exist stops being a small handful of worlds hugging their stars and becomes something far larger and more thrilling, because every gas giant with an oddly orbiting moon becomes a candidate to hide a warm sea in the dark. We even have a nearby example of tidal heating running at full, ferocious power, which helps make the idea concrete. Around Jupiter there is a moon named Io, caught in a similar gravitational tug-of-war with its neighbouring moons, flexed so violently by Jupiter's immense gravity that its entire surface is covered in erupting volcanoes, the most volcanically active body in the whole solar system. Io is not warmed by the sun either. It is warmed, and in fact turned inside out, by nothing more than the relentless gravitational kneading of its orbit. Enceladus is a gentler, colder cousin of that same process. Where Io's tidal heating drives molten rock to the surface, Enceladus's more modest furnace does something quieter and, for our purposes, far more interesting. It melts ice into water and keeps a sea from freezing, and the timescales involved are almost impossible to feel, but they matter. This flexing, this squeeze and release rhythm, has very likely been running for hundreds of millions of years, and possibly for billions, far longer than there has been anything more complicated than single cells on the Earth. That is the crucial point for the question of life. A warm environment that lasts only a moment, geologically speaking, gives chemistry no time to do anything interesting. But an ocean kept warm and stable and chemically active for hundreds of millions or billions of years is a different matter entirely. That is the kind of patience in which, on our own planet, simple chemistry once assembled itself step by step into the first living things. Time is one of the quiet ingredients of life, and Enceladus, it appears, has had a great deal of it. What makes tidal heating so remarkable, when you really absorb it, is that it is a way of getting warmth for free from the mere geometry of an orbit. There is no fuel being consumed in any ordinary sense, no fire, no store of chemical energy running down. The heat comes from the gradual transfer of energy out of the Moon's orbital motion and its neighbours, bled off slowly as friction over immense spans of time. As long as Enceladus keeps circling Saturn on its slightly stretched path, kept stretched by its rhythmic meetings with Dione, the flexing continues and the warmth keeps coming. It is one of the closest things nature has to a furnace that never needs to be fed, and it is the reason an ocean can survive in a place where, by the reckoning of sunlight alone, no ocean has any right to be. It is a strange comfort, in a way, to know that the warmth of that ocean is drawn from something as steady and ancient as an orbit. Fires burn out, fuel runs dry. But the slow gravitational rocking of a moon between a giant planet and a sister world is the kind of thing that lasts across geological ages, patient and reliable, asking nothing and giving heat for as long as the dance goes on. Whatever is happening in the ocean of Enceladus has not had to survive on a flickering, unreliable warmth. It has had a furnace that keeps its own time, turning the mere shape of an orbit into the difference between a frozen tomb and a living sea. But warmth and water, on their own, are only the beginning of the story. A warm ocean is a wonderful thing, but it is not by itself a living thing or even a promising one. Plenty of warm water has existed in the universe without ever hosting anything more interesting than minerals. What turned Enceladus from a scientific curiosity into arguably the most important target in the search for life beyond Earth was not the water and not the warmth. It was what we found dissolved in the water when, against all odds, we managed to reach out across 1 billion miles and taste the ocean directly. Because Enceladus, unlike almost every other ocean world, does not keep its sea locked away where we cannot reach it. It throws its ocean into space, every second of every day. And a spacecraft, if it is brave enough and flies low enough and fast enough, can fly straight through that spray and find out exactly what an alien ocean is made of. Part 6. Tasting an Alien Sea. Here is what makes Enceladus so precious, and so different from every other world where we suspect a hidden ocean might lie. On most of those worlds, the water is sealed away where we cannot get to it. Think of the other ocean moons we know of, worlds like Europa around Jupiter, or the giant moons Ganymede and Titan. Each of them is thought to hide a sea beneath its crust, but that sea is buried under miles of ice and rock, utterly unreachable without landing a spacecraft and somehow drilling down through a frozen shell thicker than any drill we have ever built could pierce. To sample those oceans, we would have to send a mission to melt or bore its way through miles of ice, a feat far beyond anything we can currently do. But Enceladus does something none of the others do. It hands its ocean to us, for free, continuously, flinging fresh seawater up through those south polar cracks and out into space where anything passing by can catch it. All you have to do is fly through the spray. And that is exactly what Cassini did, again and again, in some of the most daring maneuvers of the entire mission. The spacecraft was commanded to fly directly through the plumes erupting off the South Pole, threading through the geysers at tremendous speed so that its instruments could catch the ice grains and gas and measure what they were made of. In the year 2008, during a close pass, Cassini tore through the plume at nearly 18 kilometers per second, more than 40,000 miles per hour, and used an instrument called the Cosmic Dust Analyzer to catch individual grains of ice that had left the ocean only minutes before. Think about what that means. A machine built by human hands, launched from Earth years earlier, reached out and caught droplets of an alien sea that had been liquid water underground moments earlier, still fresh, still carrying whatever the ocean carried. Then, in the year 2015, Cassini performed an even bolder dive, dropping to within about 30 miles of the surface, roughly 50 kilometers, and flying straight through the densest, thickest part of the plume, using a different instrument, the ion and neutral mass spectrometer, to weigh the individual gases streaming out of the ground. In effect, a robot from Earth leaned over the edge of another world and tasted its ocean, and the first things it tasted were promising but modest. There was water, of course, the overwhelming bulk of the plume, confirming everything we suspected about the sea below. There were salts, the same kinds of salts you would find in Earth's oceans, telling us that this alien sea is in contact with rock, dissolving minerals out of a seafloor just as our oceans do. And there were simple organic molecules, small carbon-based compounds like methane drifting in the spray. Each of these was a genuine clue, another piece of evidence that the ocean of Enceladus was a real, chemically active sea and not just a sterile pocket of meltwater. But none of them, on their own, was the kind of thing that makes scientists sit bolt upright in their chairs. Salt and simple carbon are common in the universe. The real shock, the finding that transformed how the entire scientific community thought about this moon, came from that daring 2015 dive, and it was a gas. During that low, high-speed pass through the plume, Cassini's mass spectrometer detected molecular hydrogen gas, streaming out of the ocean of Enceladus in significant measurable quantities. And hydrogen gas, produced steadily and continuously, is not just another ingredient, it is a fingerprint, and it points to something specific happening on the floor of that hidden sea. Because on Earth, we know exactly what makes hydrogen gas bubble up out of the bottom of an ocean. It is produced when hot water comes into contact with certain kinds of rock far down on the seafloor, in a chemical reaction between water and minerals that releases hydrogen as a byproduct. The presence of hydrogen pouring out of Enceladus was the first strong sign that the moon's ocean is not just a bubble of water sitting on cold dead rock. It was evidence that the water is touching a warm, chemically active seafloor, that water and rock are reacting down there right now, and that the whole system is alive with chemistry in a way that, on our own planet, has a very particular and very important meaning. To understand why the scientists who saw that hydrogen reading grew so excited, you have to understand what that same reaction does on Earth, and where it does it, because it turns out that the exact chemistry Cassini smelled in the plume of Enceladus is, on our own planet, the beating engine of some of the strangest and most important ecosystems we have ever found. And those ecosystems taught us something that completely changed the rules of where life can survive. They taught us that life does not actually need the sun. It never strictly did. What it needs is water and heat and the right chemistry pouring out of rock, and if it can get those three things, it can build a thriving, crowded world of living creatures in total darkness at the bottom of an ocean where sunlight has never reached and never will. We found those worlds on the floor of our own sea, and once we understood them, we could never again look at a warm, chemically active, sunless ocean like the one inside Enceladus and honestly call it dead. The daring of these plume dives is easy to understate, so let me be clear about what Cassini actually did. Flying a spacecraft through a geyser might sound gentle, but at those speeds, it is anything but. Threading the plume at 18 kilometers per second means the ice grains were slamming into the instruments with tremendous force, and the engineers had to be certain the spacecraft could survive the barrage without being damaged, all while pointing its instruments precisely enough to catch and measure particles smaller than specks of dust, during a pass that lasted only minutes. There were no second chances on a given flyby. The geometry had to be perfect, the timing exact, the instruments ready. And Cassini did it repeatedly, each pass tuned to sample a different part of the plume, building up over years a chemical portrait of an ocean nobody could see. And the significance of the hydrogen, once it was found, is worth making very concrete, because it is not obvious why a simple gas should be so thrilling. Hydrogen gas is, in the language of biology, food. It is a source of chemical energy that living things can consume. At the hydrothermal vents on Earth's ocean floor, whole ecosystems are built on microbes that combine hydrogen with carbon dioxide to make methane and, in the process, extract the energy they need to live. When Cassini detected hydrogen streaming out of Enceladus in quantity, it was not just detecting a gas, it was detecting a potential meal, an energy source flowing continuously into the ocean, the same energy source that feeds sunless life on our own planet. The ocean of Enceladus, in other words, is not just warm and wet. It appears to be a place where something could eat. Think about what it means that we have, in a sense, already been to this ocean. We have not landed on Enceladus. We have not drilled through its ice or lowered anything into its sea, and yet, through those plume dives, material from that alien ocean has physically passed through the instruments of a spacecraft we built, been measured atom by atom, and had its chemistry read and sent home. In the entire history of our species, there are only a handful of places beyond Earth whose actual substance we have held and analysed, and most of them are rocks, the moon, a few asteroids, meteorites that fell to the ground. The ocean of a moon of Saturn is on that very short list, not because we went and scooped it up, but because the moon threw it to us, and we were there, flying through the spray, ready to catch it. Every one of those daring passes was, in effect, a conversation with a world that cannot speak. Cassini asked its question by flying through the spray, and the ocean answered in the only language it had, the chemistry of its own frozen droplets, caught and weighed in the dark. Over years, those answers accumulated into something coherent, a portrait of a sea we have never seen, assembled entirely from what it flung into space. And the more the picture filled in, the harder it became to look away from where it was pointing, because every new answer said the same thing more loudly than the last. This is not a dead ocean. This is a place where something could live. So before we go any further into what else Cassini found dissolved in that alien water, we need to go down, all the way down to the bottom of Earth's own ocean, into the black and the crushing pressure where no light has ever shone, and meet the creatures that live there. Because they are the reason a frozen moon at the edge of the Saturn system is now, in the minds of many scientists, the single most promising place in the entire solar system to go looking for a second, separate origin of life. And once you have seen what thrives around a crack in the seafloor here on Earth, you will never think about that little white moon the same way again. Part 7. The Ingredients of Life. Before we descend into the black water, we have to clear up a confusion that trips up almost everyone, because it sits at the exact center of this story, and getting it wrong is how people either overhype these discoveries or dismiss them entirely. When scientists announce that they have found organic molecules somewhere out in space, on a comet, in a cloud between the stars, or in the plume of Enceladus, a lot of people hear the word organic and immediately think living. That is not what the word means in chemistry. In chemistry, organic does not mean alive, and it does not mean from a living thing. It means, simply, a molecule built around carbon. Carbon is the element that life on Earth is based on, which is why the word carries that association. But carbon compounds form all over the universe through ordinary chemistry, with no life involved whatsoever. So finding organic molecules by itself is not the same as finding life, or even necessarily a strong hint of it. Simple organic molecules, in fact, are almost boringly common. Methane, ethane, small chains of a few carbon atoms, these things are everywhere. You find them on dead, sterile asteroids that have never hosted anything alive. You find them floating in cold clouds of gas and dust drifting between the stars, where no biology has ever existed. You find them in the atmospheres of lifeless worlds. The universe makes simple organic molecules the way it makes rocks, through plain physics and chemistry, in enormous quantities, without any need for living things to be involved. So when Cassini's early passes through the plume of Enceladus turned up simple organics like methane, that was interesting, another sign of an active chemical sea, but it was not, on its own, a reason to think anything was living down there. Simple carbon molecules are the background noise of the cosmos. They do not by themselves mean biology. What matters, what actually moves the needle, is complexity. The question is not whether there is carbon chemistry, but how large, how intricate, and how structured that carbon chemistry is. Because there is a profound difference between a simple molecule of a few atoms and the elaborate, heavy, ringed, and chained architectures that living chemistry is built from. The molecules that make life work, the amino acids that assemble into proteins, the components that build cell membranes and carry genetic information, these are large, complicated structures, and they are difficult to make. You do not get them easily. You get them either through the specific machinery of life, or through a chemical environment that is unusually crowded, energetic, and productive. The kind of environment where a lot of complex chemistry is being driven forward by a steady supply of heat and raw materials. So the real question about Enceladus was never simply, is there organic material in the plume? The real question was, how complex is it? How far along the road from simple carbon toward the machinery of life has the chemistry of this ocean actually travelled? In the year 2018, a landmark analysis of Cassini's plume data answered that question, and the answer was staggering. When scientists carefully studied the heaviest particles Cassini had caught coming off the moon, they found not simple little molecules but complex organic macromolecules. These were heavy, intricate structures, each one containing hundreds of atoms, arranged into rings and chains of carbon, with molecular masses well above 200 atomic units, which in the world of these measurements is enormous. These were not the background noise of the cosmos. These were the heavy-duty chemical scaffolds, the kind of large, structured carbon architecture from which the building blocks of life are assembled. From molecules like these, you can go on to build amino acids. From amino acids, you can build proteins. From proteins, in principle, you can build the working parts of a living cell. Enceladus was not merely venting simple carbon into space. It was venting large, complex, life-relevant organic chemistry, manufactured somewhere down in the dark beneath the ice, and thrown up into space where a passing spacecraft could catch it and weigh it. Take a moment and let the real weight of that settle, because it is one of the most quietly staggering facts we have learned about the universe in our lifetimes. The chemistry of life is not waiting to begin on Enceladus. It is already underway. Somewhere in that black ocean, under miles of ice, 900 million miles from the sun, warm water is moving over rock and assembling the same kinds of large, complex carbon molecules that, on the early Earth, came together in the long chain of steps that eventually led to the first living things. No one lit a fuse to start this. No one is watching it happen. It has simply been going on quietly and continuously for what may be hundreds of millions or even billions of years in a place that no light has ever reached and no human eye has ever seen. The ingredients of life being stirred together in the dark right now, on a moon we only learned had an ocean at all within the span of a single human lifetime. And here is the part that should keep you awake, the honest edge of the whole thing. We do not know whether that stirring ever crossed the line. We do not know whether all that complex chemistry, all that assembling of life's raw materials in a warm, dark sea, ever took the further step from chemistry into biology, from ingredients into something alive. It might have. The conditions appear to be there. Or the ocean might be a place where the chemistry endlessly builds and breaks these molecules without ever tipping over into life. A kitchen forever preparing ingredients for a meal that is never cooked. We simply cannot tell from what we have measured. But sit with the size of the question. If the same chemistry that led to life on Earth is running right now inside another world in our own solar system, our neighbour, close enough to reach with our own machines, then the origin of life may not be a rare miracle that happened once against impossible odds. It may be something the universe does readily, wherever it gets water, heat, and time. And if that is true, then the number of living worlds out there in the dark could be beyond counting. To feel the difference between simple and complex organic molecules, picture the difference between a single brick and a cathedral. Both are, in a sense, made of the same basic material, but one is just a lump, and the other is an intricate structure that took enormous organization to build. A molecule of methane is one carbon atom with a few hydrogens attached, the simplest brick imaginable, and the universe makes it everywhere, effortlessly. A complex organic macromolecule of hundreds of atoms arranged into interlocking rings and chains is the cathedral. A structure so elaborate that it does not assemble by accident in just any environment. It requires a place where energy and raw materials are being pushed together in productive, sustained ways, the kind of place where chemistry is being driven forward rather than just sitting still. And the specific masses matter here, so it is worth being precise. The heavy molecules Cassini found in the plume had masses above 200 atomic units, and some fragments pointed to parent molecules far larger still, thousands of atomic units in size. In the world of these measurements, that is enormous. These are not the small stray carbon compounds you find drifting in a cold cloud between the stars. These are large, structured, information-laden molecules, the kind that, on the early Earth, sat directly on the road that led toward biology. Finding them at Enceladus told scientists that the ocean below the ice is not merely holding carbon, but actively organizing it, building it upward into the complicated architectures from which, given enough time and the right conditions, the machinery of a living cell can in principle be assembled. It is worth being honest that this is where hope and evidence have to be held carefully apart, because the temptation to leap ahead is enormous. Complex organic molecules are the raw materials of life, the parts from which living chemistry can be assembled. But a pile of parts is not a machine, and a set of ingredients is not a meal. On the early Earth, molecules like these existed for a long stretch of time before the first thing we would call alive ever appeared, and the exact steps in between, how non-living chemistry first crossed over into self-copying, self-sustaining life, remain one of the great unsolved questions of all of science. So finding these molecules at Enceladus does not mean life is there. It means the starting materials are there, in abundance, in a warm and active sea, which is precisely the situation from which, on our own world, life once emerged. So hold both things at once, the excitement and the caution, because that is what honest wonder actually requires. The ocean of Enceladus is manufacturing the building blocks of life. and that is genuinely one of the most remarkable facts we have ever learned about another world. And we do not know whether those building blocks ever assembled into anything living, and pretending we do would be a betrayal of the very curiosity that got us here. The right response is not certainty in either direction. It is the particular, electric feeling of standing at the edge of a question that actually has an answer that is out there, waiting, in a sea we can name and could reach. That is the possibility hanging over this little moon. And to understand why scientists take it so seriously, why they do not simply shrug and say interesting chemistry and move on, you have to understand that we have seen a version of this exact setup before, thriving and crowded with life, in the last place on Earth anyone thought to look. We found it at the bottom of our own ocean, in the cold and the dark and the crushing black, and what we found there rewrote our understanding of what life needs to exist at all. Part 8. The Vents at the Bottom of Two Oceans. To understand what might be happening on the floor of the ocean of Enceladus, scientists did something that sounds almost poetic. They looked at the floor of our own. Because for most of human history, we believed we understood the basic rule that all life obeyed. We believed that life ran on sunlight. Plants capture the energy of the sun and turn it into food, and animals eat the plants, or eat the animals that ate the plants, and so in the end nearly every living thing on Earth traces its energy back to our star. Sunlight was the foundation, the source, the thing without which we assumed no ecosystem could survive. And that belief had a clear implication for the search for life beyond Earth. If life needs sunlight, then life needs to live near the surface of a world, near a star, in the light. A sunless ocean sealed under miles of ice would be, by that logic, a dead end. Nothing could live there. There would be no energy to power it. Then, in the late 1970s, we sent submersibles down to the bottom of the Pacific Ocean, thousands of feet below the surface, into a region of total permanent darkness where sunlight has never penetrated and never will. And what we found there overturned everything. Down in that blackness, along cracks in the ocean floor where the planet's internal heat leaks up from below, we discovered hydrothermal vents, places where mineral-laden water, heated by the molten rock beneath the crust, comes pouring out of chimneys of stone and mixes with the freezing seawater around it. And clustered around these vents, in the cold and the dark and the crushing pressure, thousands of feet below the reach of any sunlight, we found life. Not scattered, struggling life, but thriving, crowded, abundant ecosystems. Forests of giant tube worms, pale and swaying, ghostly white crabs, mats of bacteria coating the rocks, entire food webs, complete and self-sustaining, in a place where the old rule said nothing should be able to survive at all. These creatures do not run on sunlight because there is none. They run on chemistry. The process is called chemosynthesis, and it works like this. The hot water pouring out of the vents is loaded with dissolved chemicals and gases pulled from far inside the Earth, and certain microbes have learned to pull energy directly out of those chemicals, feeding on the raw chemical potential, streaming from the rock the way a plant feeds on light. Those microbes become the base of the food chain, and everything else, the tube worms, the crabs, the whole strange community, is built on top of them. It is a complete ecosystem powered not by a star 93 million miles away, but by the heat and chemistry of the planet itself, welling up through a crack in the seafloor. And the discovery of these vent communities taught us something that changed the entire search for life in the universe. It taught us that life does not, in fact, require sunlight. What life requires is an energy source, and liquid water, and the right chemistry, and if it can get those, it can build a world in the dark. Now here is where it comes together, and where the chill runs down your spine. The specific chemical reaction that powers those vents on Earth, the reaction between hot water and certain iron-laden and magnesium-laden rocks, is a process called serpentinization. And when that reaction happens, when hot water reacts with that kind of rock, it produces three things. It produces heat, it produces hydrogen gas, and it produces complex organic molecules, carbon compounds assembled by the raw energy of the chemistry. Heat, hydrogen, and complex organics. Now think back to what Cassini found pouring out of the ocean of Enceladus. It found the ocean was warm. It found hydrogen gas streaming from the plume, the exact fingerprint of hot water reacting with rock. And it found complex organic molecules, the same kind of carbon architecture that serpentinization produces. Point for point, the chemistry Cassini detected coming off that little moon matches the chemistry that, on the floor of Earth's ocean, powers some of the most abundant life on our planet. The data strongly suggest that on the seafloor of Enceladus, right now, hot water is reacting with rock in exactly the way it does at our own hydrothermal vents. I want to take you down there so you can feel it, because a description on a page is one thing and standing at the edge of it is another. Imagine you're in a submersible, sinking through Earth's ocean, down past the last of the light. At first the water is blue, then a deepening grey, and then, somewhere below a few hundred feet, the last of the sunlight gives out and the world goes utterly black. You keep sinking thousands of feet down, the pressure building to a force that would crush an unprotected body flat, and there is nothing outside the window but the beam of your lights cutting into water that has never known the sun. And then, out of that blackness, something rises. A chimney of dark rock, taller than a person, taller than a house, breathing a shimmering plume of hot mineral water into the cold, and around it, impossibly, life. Pale forests of tube worms as long as your arm, swaying in the current. Blind white crabs picking their way across the stone. A whole crowded community, alive and feeding and reproducing in the coldest, darkest, most crushing place on the planet, none of it needing the sun, all of it living on the chemistry of the rock. Now hold that image in your mind and carry it 900 million miles across the solar system, out to the frozen moon beside Saturn. Picture the same total darkness. Picture the same cracks in a rocky seafloor. Picture the same hot water, loaded with hydrogen and carbon pouring up from below. Everything we can measure says that the floor of the ocean of Enceladus looks, chemically, like the floor of our own ocean where life crowds thickest. We have seen, with our own instruments, on our own planet, that life reliably gathers around vents exactly like these, that it does not need light, that it will build a thriving world around a crack in the dark if the chemistry is right. And the chemistry, as far as we can tell, is right on Enceladus. The only thing we have not been able to do is lower a light over the edge of that other ocean and look. That is the whole distance between what we know and what we long to know. We have found the vent's fingerprint on another world. We have simply not yet been able to go and see what, if anything, has gathered around them in the dark. The discovery of these vent ecosystems in the late 1970s is one of those moments when science genuinely stunned itself. The researchers aboard the submersible had gone down expecting the seafloor around the vents to be, at most, sparsely populated, because everything they had been taught said that life needed sunlight and there was none down there. Instead, they found the water around the vents teeming, crowded with creatures no one had ever seen, entire communities living in defiance of the rule that all life traces back to the sun. Biologists back on the surface, hearing the reports, initially struggled to believe it. It forced a rewrite of the textbooks, and more than that, it forced a rewrite of the imagination, expanding the definition of where life could possibly exist to include the coldest, darkest, most crushing places on the planet. And the reason this bears so directly on Enceladus is that it removed the single biggest objection to life in a buried ocean. Before the vents, anyone proposing life beneath the ice of a frozen moon could be answered with a simple, devastating question. Where would it get its energy, with no sunlight? After the vents, that question had an answer, demonstrated and undeniable, right here on our own planet. It gets its energy from the chemistry of the rock, from the hydrogen and the heat welling up through the seafloor. The vents did not just reveal strange creatures in our own ocean. They handed the search for life beyond Earth a working model, a proof that a sunless, ice-covered sea with hot chemistry at its floor is not a dead end at all, but exactly the kind of place where life once started can flourish in the dark. There is a deeper lesson in those vent creatures that reaches beyond the question of energy. They show that life, once it takes hold, is astonishingly inventive about where it will live. We used to imagine life as a fragile thing that needed gentle, sunlit, temperate conditions, something like a garden. The vents taught us otherwise. Life on Earth thrives in boiling water, in crushing pressure, in total darkness, in acid, in places that would kill a human being instantly, wherever there is energy to be had and liquid water to swim in. If life is that stubborn and that adaptable on our own planet, then the sunless, high-pressure, chemically active ocean of Enceladus, far from being too harsh for living things, looks like exactly the kind of place where Earth's own hardiest organisms would feel right at home. When you carry the image of those crowded, thriving vents back to Enceladus, the frozen moon stops looking like a frozen moon at all. It starts looking like a promising address. We know, from our own ocean floor, exactly what kind of neighbourhood forms around hot chemical vents in the sunless dark, and it is not a barren one. It is one of the most densely populated neighbourhoods on our planet, and every measurement Cassini made says the seafloor of Enceladus offers the same kind of neighbourhood, the same warmth, the same chemistry, the same energy welling up through the rock. We have seen who moves in when those conditions appear here. The only question left is whether anyone has moved in there. And here is why that possibility is taken so seriously, rather than dismissed as wishful thinking. The discovery of life around Earth's own vents is the single reason we can look at a frozen moon and seriously, soberly ask whether it is inhabited. Before we found those sunless ecosystems, a buried ocean would have been an obvious dead end. After we found them, a buried ocean with warmth, water, and vent chemistry became one of the most promising places imaginable. Our own darkest, strangest ecosystems are the proof of concept for the entire search. They are the reason a plume of mist off a dead-looking moon can make a serious scientist's pulse quicken. But warmth and water and vent chemistry, as astonishing as they are, still are not the whole recipe. Life on Earth needs a specific short list of chemical ingredients, 6 of them, and for years, even as the case for Enceladus grew stronger and stronger, 2 of those 6 essential ingredients stubbornly refused to show themselves. Until we found them, the recipe was incomplete, and the question of whether Enceladus truly had everything life needs remained open. Part 9. The Recipe. Astrobiologists, the scientists who study the possibility of life beyond Earth, have a way of checking whether a given world has what it takes. They look for a specific chemical recipe, a short list of the essential elements that all known life is built from, and it has a name that works as an acronym, a word made from the first letters of each ingredient. The word is CHNOPS, spelled CHNOPS, and it stands for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 elements are the essential building blocks of every living thing that has ever existed on Earth. Every cell, every strand of genetic material, every protein, every membrane is assembled from these 6 ingredients. Find all 6 of them available in a warm, wet, energetic environment, and you have found a place that has, at minimum, the raw chemical shopping list that life requires. Miss even one, and the recipe is incomplete, and the case for habitability has a hole in it. For years, as Cassini flew through the plume of Enceladus again and again, scientists were quietly checking off the ingredients one by one, and the list was filling in with remarkable ease. Carbon was there, obviously, in all those simple and complex organic molecules the spacecraft had detected. Hydrogen was there, both in the water itself and streaming out as that telltale hydrogen gas from the vents below. Nitrogen was there, detected in the compounds coming off the moon, and oxygen was there in abundance, bound up in the water molecules that make up the overwhelming bulk of the ocean. 4 of the 6 essential elements, carbon, hydrogen, nitrogen, and oxygen, were found in the early flybys, and each one strengthened the case that Enceladus was not just a warm ocean, but a chemically complete one, an ocean stocked with the fundamental ingredients of biology. 4 out of 6 is a remarkable haul from a moon 900 million miles away that we were sampling by flying a spacecraft through its spray at 40,000 miles an hour. But 2 of the 6 held out, and they were not minor omissions. They were, in some ways, the 2 that mattered most. Phosphorus and sulfur remained frustratingly elusive, missing from the data, undetected in the plume, and their absence left a real gap in the argument. And of the 2, phosphorus was the one that truly mattered. The one whose absence gnawed at the scientists because phosphorus is not just one ingredient among many. It occupies a place of singular importance in the chemistry of life, and without it, no life as we understand it can exist at all. So even as the case for Enceladus grew more and more compelling, even as the warmth and the water and the hydrogen and the complex organics all fell into place, there was this stubborn hole in the recipe, this one critical element that we had every reason to expect but could not actually find. And until we found it, the honest scientific position had to include an asterisk. Enceladus had almost everything. It did not yet have everything. Let me explain why phosphorus specifically is such a big deal, because once you understand what it does, you understand why its absence was so unsettling, and why finding it would matter so enormously. Phosphorus is the backbone of the molecule that carries the genetic code of every living thing. When you picture the famous double helix, the twisting ladder of genetic material that holds the instructions for building an organism, the two long rails of that ladder, the structural spine that holds the whole thing together, are built from phosphorus. Without phosphorus, there is no genetic material, no way to store or copy the instructions of life, and phosphorus does something else just as vital. It is the core component of the molecule that every single living cell uses to store and transfer energy, the tiny rechargeable battery that powers the machinery of life at the smallest scale. Every time a cell does anything, moves, grows, divides, builds a protein, it spends energy in the form of that phosphorus-based molecule. Life on Earth, at its most basic level, runs on phosphorus. It is not optional. It is not a nice to have. It is structural, essential, non-negotiable. So this was the situation as it stood for years. Enceladus had a warm, worldwide ocean, kept liquid by the endless flexing of tidal heat. It had a chemically active seafloor with hot water reacting with rock, producing hydrogen and heat in exactly the pattern that powers life at Earth's own vents. It had complex organic molecules, the heavy scaffolds from which the machinery of life is built. It had 4 of the 6 essential elements confirmed directly in its spray. Every piece was falling into place one after another, building a case that grew harder and harder to dismiss. And yet the single most critical remaining ingredient, the phosphorus that forms the spine of genetic material and the core of the cell's energy supply, had not been found. It was the missing piece at the very center of the puzzle, the one element whose presence or absence could tip the whole question one way or the other. Scientists had every theoretical reason to believe it should be there in that alien ocean. They simply had not yet been able to prove it. Each of these 6 elements plays a role so fundamental that life as we know it cannot proceed without it, and it is worth naming what they do. Carbon is the scaffold, the element whose ability to form long chains and rings makes the complex molecules of life possible in the first place. Hydrogen and oxygen make up water itself, the solvent in which all of life's chemistry takes place, and they thread through nearly every biological molecule besides. Nitrogen is essential to the amino acids that build proteins and to the very code of genetics. Sulfur helps proteins fold into their working shapes, and phosphorus, the last holdout, forms the backbone of genetic material and the currency of cellular energy. Take any one of these away and the whole system fails. They are not a wish list. They are a hard requirement, checked off in the chemistry of every organism that has ever lived on Earth. So the years-long hunt for these ingredients in the plume of Enceladus was, in a very real sense, a search for completeness. Each element found was a box checked, a piece of the argument locked into place, and with carbon, hydrogen, nitrogen, and oxygen confirmed, the case was already strong. But a recipe with holes in it is still a recipe with holes, and a careful scientist could not, in honesty, call the ocean of Enceladus fully stocked for life, while the phosphorus that anchors genetics and energy remained unaccounted for. It was the difference between a kitchen that has most of what a meal requires and one that has everything. And in a search this consequential, where the stakes are nothing less than whether we are alone in the universe, that difference between most and everything was not a detail to be waved away. It was the whole remaining question. Notice what the search for these 6 elements really represents, because it is a quietly profound way of looking for life. We are not, at this stage, looking for creatures. We are looking for the conditions under which creatures become possible, checking whether a distant environment has the same chemical foundation that our own biology is built on. It is a bet, in a sense, that life elsewhere would be built from the same basic ingredients as life here, and it is a reasonable bet because these 6 elements are common in the universe and have chemical properties that make them uniquely suited to building the complex, flexible molecules that any life would seem to need. When we tick the boxes on that list for another world, we are asking whether the universe has, in another place, laid out the same table it once set here. There is a humbling symmetry in searching another world for the same 6 elements that make up your own body. The carbon in your cells, the phosphorus in your genes, the nitrogen in your proteins, the very water you're mostly made of, all of it is drawn from that same short list, the same handful of ingredients we go looking for in the spray of a distant moon. To ask whether Enceladus has the chemistry of life is, in a sense, to ask whether it has the chemistry of you, and the answer, ingredient by ingredient, kept coming back the same. Yes, yes, yes. Right up to the last, most critical element, the one that took the longest to find and mattered the most, and then, in the year 2023, they proved it. A discovery came out of a fresh look at Cassini's old data that filled in the last critical gap and completed the recipe in a way that made headlines around the world, because it took the case for Enceladus from compelling to nearly complete. The final ingredient, the one that mattered most, the one that had held out the longest, turned out to be there after all, and not just there, but present in a concentration that stunned the researchers who found it. What Cassini had captured in the spray of that little moon, waiting all along in data that had already been collected years earlier, was about to turn Enceladus from the most promising candidate for life beyond Earth into something even more remarkable. The last lock on the door was about to click open. Part 10. The Last Ingredient. The breakthrough came, as many of the best discoveries about Enceladus have, not from a new spacecraft, but from a fresh and patient look at data Cassini had already sent home. The spacecraft's mission had ended in the year 2017, when it was deliberately steered into Saturn to burn up in the atmosphere, but the enormous archive of measurements it had gathered over 13 years at Saturn remained, waiting to be mined by anyone clever enough to ask the right question of it. And in the year 2023, a team of researchers went back to a particular set of measurements, the readings from the ice grains that had escaped Enceladus and spread out to form Saturn's E-ring, the faint outer ring made of the moon's own frozen ocean spray. By studying those grains with painstaking care, weighing the chemistry of the salt-laden ice particles that the moon had flung into space, they finally found the ingredient that had held out the longest. They found phosphorus. Specifically, they found phosphates, phosphorus bound up with oxygen in exactly the dissolved, usable form that life on Earth relies on, present in the ice grains that had come from the ocean of Enceladus. And it was not a trace, not a faint whisper at the edge of detection that might be argued away. The concentration was extraordinary. The researchers calculated that phosphate is present in the ocean of Enceladus at levels at least 100 times higher than in Earth's own oceans, and possibly as much as 1,000 times higher. Sit with that comparison for a moment. This distant frozen moon does not merely contain the rarest and most critical ingredient for life. It contains it dissolved in its sea at a concentration that dwarfs what is available in the ocean here on our own living planet. The one element whose absence had left a hole at the centre of the argument turned out to be not just present, but wildly, generously abundant, more available in that alien ocean than in the waters where life on Earth actually arose. With that discovery, the recipe was, for all practical purposes, complete. Let me lay it out one more time, all together, so you can feel the full weight of what we now know. Enceladus has liquid water, an entire global ocean of it, 6 miles from top to bottom in places. It has a steady, reliable source of heat, the tidal furnace driven by the endless flexing of the moon in Saturn's grip, keeping that ocean warm without any need for the sun. It has a chemically active rocky seafloor, where hot water reacts with rock to produce hydrogen gas, the same reaction that powers thriving ecosystems in the darkness of Earth's own ocean floor. It has complex organic molecules, the heavy carbon scaffolds from which the machinery of life is assembled, and now, with the phosphorus found, it has the full complement of the 6 essential elements of life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The entire Carnop's recipe, available in a warm, wet, energetic sea. Every single thing that we know life requires, as far as we're able to measure from 900 million miles away, is present in the ocean of this little moon. Stop here, because this is the emotional centre of the entire story, the place where the facts stop being merely impressive and start being almost unbearable to think about. Every ingredient is there, the environment is ready, the water is warm, the chemistry is churning, the nutrients are dissolved in abundance, the energy is flowing from the vents, and the raw materials of biology are being assembled and thrown into space where we can catch them. The recipe is complete, and the kitchen is warm, and everything needed for the meal is laid out on the counter. And we do not know if anyone is cooking. We do not know whether, in all that readiness, in all those hundreds of millions or billions of years of a warm sea, stocked with everything life needs, life ever actually began. It might have. Everything is in place for it. Or the ocean might be a place where all the ingredients sit together forever, without ever combining into something alive, a perfect kitchen with no cook, a recipe with no one to make it. And the maddening, thrilling truth is that from everything we have measured, we genuinely cannot tell which of those two it is. This is the strange new kind of loneliness that Enceladus has given us, and it is worth naming honestly. For most of human history, the question of life beyond Earth was pure speculation, a matter of philosophy and imagination, with no way to test it and nothing concrete to point to. Now it is different. Now there is a specific place, a real world with a name, close enough to reach with machines we already know how to build, where every precondition for life has been checked and confirmed, and where the only remaining question is whether the line from chemistry to biology was ever crossed. The answer is not out among distant stars forever beyond our reach. The answer is in our own solar system, in a sea we can name and measure and in principle visit. It is almost certainly already down there one way or the other, a yes or a no written into that dark ocean, waiting. We have narrowed the greatest question our species has ever asked down to a single frozen moon, and we have not yet been able to go and read the answer. There is something poetic about where the phosphorus was hiding, and it ties back to a fact we noted much earlier. The researchers did not find it by sending a new probe. They found it in the ice grains of Saturn's E-ring, the faint outer ring made almost entirely of Enceladus's own frozen ocean spray, the material the moon has been paving its orbit with all along. In other words, the last and most critical ingredient of life had been circling Saturn in plain sight, spread out into a ring, waiting in data Cassini had already gathered years before anyone thought to look for it there. The moon had been mailing us the answer the entire time, scattered across a ring wider than a planet, and we simply had not yet opened the letter and read it closely enough, and the sheer abundance of it reframes the whole picture. Phosphorus is famously scarce on Earth. It is often the limiting ingredient for life in our own oceans, the nutrient that runs out first, the bottleneck that caps how much life a given patch of sea can support. Farmers spread phosphorus on their fields precisely because there is never enough of it to go around. To find it in the ocean of Enceladus, not just present, but 100 to 1,000 times more concentrated than in Earth's seas, is to find that the one ingredient most likely to hold life back is, on this frozen moon, wildly overstocked. Whatever else can be said about the ocean of Enceladus, it is not going to run short of the element that anchors genetics and powers cells. The pantry is not merely full. On this particular shelf, it is overflowing. And this is the moment where the whole long argument finally closes, where every separate thread we have followed ties together into a single knot. The water, the warmth, the salt, the reactive seafloor, the hydrogen, the complex organics, and now the phosphorus, all of them confirmed, all of them present in one small ocean at the edge of the Saturn system. For the first time in the history of our search, we could point to a specific world beyond Earth and say, with real evidence behind every word, that it has everything we know life requires. Not most of it, not probably, everything as far as we are able to measure. That had never been true of any other place. Mars, for all its promise, is dry and cold and battered. The other ocean moons keep their seas locked away. Enceladus alone laid its whole chemistry bare and passed every test. Let that fact stand on its own for a moment, stripped of all qualification because it deserves to. There is right now a world in our solar system that has every known ingredient for life dissolved in a warm, dark, moving sea. Not a world we're guessing about. A world we have measured, tasted, and confirmed. It is close enough to reach with machines we already know how to build, and it has been sitting out there, fully stocked and quietly active, for perhaps billions of years, through the entire rise of life and civilization on Earth, waiting in the cold beside Saturn for us to grow curious enough and capable enough to come and find out what it has been doing all this time. But the story does not stop even there, because there was one more discovery still to come, one that took the ocean of Enceladus from a place that might have hosted the chemistry of life at some point in the past to a place that is unmistakably, vigorously active right now, in the present tense, as you listen to these words. Because the most recent look at Cassini's data found something that could not have survived long in space, something so fragile that its very presence proved the ocean's chemistry was still running, still building, still fresh, at the moment the spacecraft flew through the spray, and that discovery changes the tense of everything from what the ocean once was to what the ocean is doing tonight. Part 11. Fresh from the ocean. In the latter part of the year 2025, researchers went back once more to Cassini's records, this time to the data from one of the spacecraft's fastest and most violent passes through the plume, that high-speed flyby back in 2008, when it had torn through the spray at nearly 18 kilometers per second, and caught fresh ice grains with its cosmic dust analyzer. Using new techniques and a more careful analysis than had been possible before, they pulled out the chemical signatures hidden in those grains, and they found molecules that had never been clearly identified in the plume before. They found members of chemical families with names like esters and ethers, and they found alkenes, some of them arranged in rings, along with hints of nitrogen-bearing compounds. These are not exotic curiosities. Esters and ethers, in particular, are the kinds of molecules that can form parts of lipids, and lipids are the fatty molecules that make up the membranes of every living cell, the boundaries that separate a cell from the world around it. Finding these particular molecules in the spray of Enceladus was another step up the ladder of complexity, another set of life-relevant building blocks confirmed present in that ocean. But the truly important thing about this discovery was not just what the molecules were, it was what their presence proved about timing. Because these particular organic molecules are fragile. They are delicate structures that do not last long once they are exposed to the harsh environment of space, where radiation and time break such molecules apart relatively quickly. And this is the key that unlocks the whole significance of the finding. The grains that carried these fragile molecules had been caught mere minutes after they left the ocean, sampled just 13 miles from the surface, still fresh from the vent. If these delicate molecules had been made long ago and had been drifting in space for ages, they would have been destroyed. The fact that Cassini caught them intact, in fresh grains, means they had been synthesized in the ocean only a short time before they were ejected. In other words, these molecules were not ancient relics, they were newly made. The chemical factory on the floor of the ocean of Enceladus was not something that ran once, long ago, and went quiet. It was running at the very moment Cassini flew through the plume. The vents are active now, the chemistry is happening now. The ocean is, in the most literal sense, alive with activity in the present tense, and we do not have to rely only on decade-old data from a spacecraft that is no longer flying to know that Enceladus is still active. This is exactly where the James Webb Space Telescope returns to the story, closing the circle we opened at the very beginning. When Webb turned its infrared eye on Enceladus in the year 2022 and photographed that plume stretching more than 6,000 miles into space, it was not looking at a historical event. It was watching the moon do this today, in our own time, live. And Webb measured the rate, that figure of around 300 litres, close to 80 gallons, of water per second, pouring off the South Pole and feeding the whole Saturnian system. The little moon is actively, continuously at this very moment, emptying its ocean into space through those south polar cracks, exactly as it has been doing for as long as we have been able to watch, and almost certainly for an immense span of time before we ever arrive to see it. The moon is not a fossil of past activity. It is a working, breathing, presently active world. Let me take you on the journey of a single drop, because it ties the whole thing together, and it is a genuinely strange and wonderful path to trace. Imagine a droplet of water, far down in the ocean of Enceladus, near the seafloor, where hot mineral-laden water is welling up from a vent in the rock. That droplet is warm, and it carries dissolved in it the products of all that chemistry, the salts, the hydrogen, the complex organic molecules, the phosphates, the fragile esters and ethers freshly assembled in the reactions at the vent. The droplet rises, carried upward through the black water by the warmth, drifting up toward the underside of the ice shell far overhead. It finds its way into one of the cracks that reach down from the surface, one of the passages beneath a tiger stripe, and as it moves up through that narrowing channel toward the surface, the pressure drops, and near the top the water flashes, some of it turning to vapour, and the droplet is caught in a rush of gas accelerating toward the opening. It bursts out of the crack at over 800 miles per hour, out of the warm dark and into the vacuum and the cold, where in an instant it freezes into a tiny grain of ice, and that grain flies up, away from the moon entirely out into space, still carrying the fresh chemistry of the ocean locked inside it. And then, minutes after leaving the sea, a spacecraft from Earth sweeps through and catches it, and weighs it, and reads in that single frozen grain a message written by an alien ocean only moments before. That is not a metaphor. That is, in essence, exactly what happened. Enceladus mailed us a sample of its living sea, and we caught it in flight. The logic of fragility as a clock is worth making explicit, because it is a genuinely elegant piece of reasoning. Imagine you find a snowflake resting on a warm windowsill. You do not need to have watched it land to know it fell only moments ago, because a snowflake cannot survive long on a warm surface. Its very presence, intact, tells you the snowfall is recent, maybe still happening. The fragile esters and ethers in the plume of Enceladus work the same way. Because these molecules break down relatively quickly once exposed to the radiation of space, finding them intact in fresh grains sampled minutes after eruption is proof that they were made in the ocean very recently, not eons ago. Their fragility, which might seem like a weakness, is exactly what makes them such powerful witnesses. They could only be there if the ocean's chemistry was running at that very moment. And this transforms Enceladus from a story about the past into a story about the present, which is a profound shift. It would be one thing to say that, long ago, the ocean of this moon was warm and chemically active, and might once have hosted the beginnings of life, a fossil possibility, a door long since closed. It is another thing entirely to say that the ocean is warm and chemically active right now, tonight, as these words reach you, its vents working, its chemistry building fresh molecules, its geysers actively flinging that fresh chemistry into space, where our telescopes can watch the plume glowing in infrared light. Whatever is or is not alive in that sea, the sea itself is unmistakably active in the present tense. Enceladus is not a monument to something that might have happened. It is a process still underway, and that means the answer we are looking for, if it exists, is not a relic to be excavated. It is a living thing to be found. There is a phrase worth holding on to here, one that captures the emotional strangeness of this moment in the search. We are, in a real sense, receiving messages from an ocean that does not know it is sending them. Every grain of ice that Enceladus flings into space is a small parcel of that sea, carrying its chemistry, its temperature history, its dissolved ingredients, frozen and preserved and hurled outward for anyone with the right instrument to read. The moon is not trying to communicate, it is simply doing what it does, venting its ocean through cracks in its ice. But the effect, for us, is that a world 900 million miles away is continuously broadcasting the contents of its hidden sea into the open, and we have only just begun to learn how to listen. This is what shifts the whole story into the present tense and refuses to let it settle. The plume Webb photographed is rising off the moon at this very moment. The vents that made those fragile molecules are working now. The ocean is warm now. Whatever is happening in that sea, whatever chemistry is unfolding in the dark, is not a closed chapter from the ancient past, but an ongoing process, running tonight, as unfinished and alive as the moment you are living through. And that means the answer we are chasing is not a fossil waiting to be dug up. It is a living circumstance, still in motion, still being written, and it will still be there, still churning, on the day we finally return to read it. This is the astonishing gift that sets Enceladus apart from every other ocean world we know. Europa, Titan, Ganymede, all of them may hide oceans as promising as this one, but they keep those oceans locked away under miles of ice, unreachable without technology we do not yet possess. Enceladus alone throws its ocean into space for us to catch, freely and continuously, a moon that is, in effect, paving its orbit with samples of its own sea and inviting anyone passing by to read them. We have already caught those samples. We have already read them, as far as our instruments allowed, and everything written in them, every molecule, every element, every chemical fingerprint says the same thing. This is a warm, active, chemically loaded ocean, running the machinery of prebiotic chemistry right now, stocked with every ingredient life requires, apparently touched by hydrothermal vents of the exact kind that crowd with living things on our own planet. Everything says this is a place where life could exist. And yet, after all of it, after 2 decades of flybys and daring plume dives and painstaking reanalysis, we still cannot say whether life actually does exist there. And the reason we cannot say is almost painfully simple, and it is where our story has to end. Part 12. The Eyes We Didn't Give It. If the ocean of Enceladus is so perfectly primed for life, if it is churning out the exact chemicals that biology needs, warm and wet and stocked with every ingredient, then there is an obvious question that you have probably been holding on to this whole time. Why didn't Cassini just find the life itself? Why, after flying through the plume again and again, after tasting the ocean directly, did the spacecraft not simply detect the living things, if they are there? The answer comes down to engineering, and it is one of the quietly heartbreaking facts of modern space exploration. Cassini could not find alien life because we never gave it the eyes to see it. It was searching for the smoke, and it had no instrument built to look for the fire. Remember what Cassini was. It was designed and built in the years before it launched in 1997, conceived as a mission to study a planet, its rings, its weather, and its magnetic field. It was in essence a weather and geology satellite for the Saturn system, an extraordinary one, but built for a specific set of jobs. Its instruments were designed to weigh molecules, to measure magnetic fields, to photograph clouds and rings, to identify the basic chemistry of gas and dust. And it did all of those things brilliantly, far beyond what anyone expected, which is the only reason we know any of this story at all. But it carried no microscope. It had no way to capture a sample and search it for cells. It had no instrument capable of imaging a living organism or reading a strand of alien genetic material. When it flew through the plume, it could tell you the mass of the molecules in the spray and identify the elements present, and that is how we learned about the water, the salts, the organics, the hydrogen, the phosphorus. But it simply lacked the specific technology required to detect a living cell, because when it was built, nobody was designing it to find life at Enceladus. Nobody yet knew there was an ocean there to search. So Cassini found the smoke. It found every indirect sign, every telltale trace, every fingerprint of a place where life could be. It found the warmth and the water and the chemistry and the energy and the ingredients. It found, in the end, one of the most beautifully complete pictures of a potentially habitable environment that we have ever assembled for any world beyond Earth. But it could not find the fire itself, the living thing, the actual organism, because it was never given the instrument to look. And here is the honest place we have to stand, the line we must not cross even though everything in us wants to. Everything we have learned tells us that Enceladus is habitable, that it has all the conditions life requires. But habitable is not the same as inhabited. A place can have everything life needs and still be empty. The presence of every ingredient does not guarantee the presence of life. It only guarantees the possibility. And the difference between those two things, between could and does, between habitable and inhabited, is the single most important unanswered question this little moon has handed us. And Cassini, for all its genius, was simply not built to answer it. What we need now is to go back. What we need is a next-generation spacecraft, one designed from the beginning with the specific goal of searching for life, carrying the microscopes and the sample analyzers and the biology instruments that Cassini never had, sent to fly through those same plumes, or even to land beside a tiger stripe and lower an instrument toward the edge of that hidden sea. We know the ocean is there. We know it sprays itself into space where a spacecraft can catch it. We know what it contains. All that remains is to return with the right eyes, to lean over the edge, and to actually look. And when we do, one of two things will happen, and both of them are staggering. Either we will find nothing and learn that a world can have every ingredient of life and remain sterile, which would tell us that the step from chemistry to biology is rarer and stranger than we hoped, or we will find something alive, a second, separate origin of life, arisen on its own in the dark ocean of a moon we very nearly dismissed as a dead pebble. And if that happens, if we find life at Enceladus, it changes everything about how we understand our place in the universe. Because think about what it would mean. Life arising twice, independently, in a single solar system, on two worlds as different as a warm blue planet and a frozen moon, would tell us that life is not a fluke, not a 1 in a trillion accident that happened here and nowhere else. It would tell us that life is something the universe does readily, wherever it finds liquid water, warmth, chemistry, and time. And those conditions, we now know, are not rare. They are hidden under the ice of cold moons all across the outer solar system, and by extension, all across the countless solar systems of the galaxy. If a small frozen moon beside Saturn holds living things in its buried sea, then the number of living worlds scattered through the universe is almost certainly beyond anything we could count. We would go, in a single discovery, from wondering whether we are alone to knowing, nearly for certain, that we never were. It is worth sitting for a moment with the particular sorrow and beauty of building a machine that finds the door but cannot open it. Cassini did everything it was asked to do and vastly more, and in the process it handed us the most complete case for a habitable world beyond Earth that we have ever assembled. But it was designed and built by people who did not yet know that Enceladus had an ocean, and so it could not carry the tools to search that ocean for life. There is no failure in this, only the ordinary limit of foresight. We built the eyes we knew how to build, pointed at the questions we knew how to ask, and the universe answered with a question we had not thought to prepare for. That is not a defeat. That is what discovery feels like from the inside, and it is precisely why we go back. Missions to do exactly that have been studied and proposed, and the concepts are within our reach. A spacecraft could be sent to orbit Saturn and fly repeatedly through the plume, this time carrying instruments designed from the ground up to detect the signatures of life, to search fresh ocean grains for the specific molecular patterns that only biology produces. A bolder mission could land beside the tiger stripes and sample the fallout of the geysers directly on the surface. We know where to go. We know the ocean sprays itself into space for us to catch. We know, from Cassini, that everything life needs is waiting in that spray. The only thing standing between us and the answer is the will to build the right machine and send it, and the patience to wait the years it would take to arrive and to listen for what it finds. There is one more thing to hold, and it is perhaps the most important of all, because it is about how to carry a question this large without either overclaiming or despairing. We have not found life on Enceladus. We must say that plainly and keep saying it, because the difference between a place that could hold life and a place that does hold life is the entire distance still to be crossed, and honesty about that distance is what makes the search worth trusting. But we have found something almost as staggering in its own right, which is a real, reachable place where the question can actually be settled, where the answer is not a matter of speculation but of going and looking with the right tools. For most of human history, the question of whether we are alone had no address. Now it has one, and the address is a frozen moon we can name. And so we are left in a rare and remarkable position for our species, standing at the threshold of an answer instead of only a question. Somewhere out past the light, on a moon that spent centuries pretending to be dead, there is a warm ocean holding in its dark water the answer to whether life is a lonely accident or a common consequence of the universe simply being what it is. The answer is already there. It has always been there. It is waiting in the cold and the silence, patient as an orbit, for the day we build the right eyes, cross the long dark, lean out over the edge of that hidden sea, and finally, after all this time, look down and see what looks back. And so we return, at the very end, to where we began, to that small white moon and the fountain rising off its south pole into the black. Remember how it looked at first, the deadest-looking world we had ever found. Blinding white, colder than almost anything imaginable, so bright and so frozen and so silent that not a single scientist thought to look at it twice. We were so sure it was dead, and it turned out to be, as far as we can measure, the most alive place we have found beyond the Earth. An ocean in motion, vents at work, chemistry churning, a whole warm world hidden beneath a mask of ice, quietly assembling the ingredients of life and mailing them out into space for anyone to read. The lesson Enceladus teaches in the end is a kind of humility and a kind of hope. It is that the universe is far stranger and far more generous with the conditions for life than we ever assumed, that warmth and water and possibility can be hiding in the coldest and most lifeless-looking places, and that the answer to the oldest question we have ever asked, the question of whether we are alone, may not be waiting among distant stars at all. It may be waiting much closer than that, in the dark ocean of a frozen moon we can almost reach, holding its answer patiently, in the cold and the silence, until the day we finally return with open eyes and lean over the edge to look.